Have you ever wondered whether pure carbon and hydrogen can spontaneously combine to form valuable hydrocarbons such as methane, ethylene, propane, and even heavier hydrocarbons? What if Aspen Plus could predict the entire product distribution without writing a single reaction equation? In this video, I will demonstrate how to simulate the production of hydrocarbons from elemental carbon and hydrogen using the Gibbs reactor model in Aspen Plus. Let's begin by defining the chemical components that are involved in the simulation. Since our objective is to investigate equilibrium hydrocarbon formation, we first define elemental carbon and hydrogen as our reactants. To capture the possible products, we include a range of hydrocarbons, including methane, ethane, ethylene, acetylene, propane, propylene, butanes, and butenes. By including multiple possible products, Aspen Plus can determine which hydrocarbons are thermodynamically favored under the specified operating conditions. This approach eliminates the need to manually define reaction stoichiometry. But how does Aspen decide which products are formed and in what amounts? We have to look at it. To accurately model this hydrocarbon system, we select the property package as RK-Soave, Redlich-Kwong-Soave, which is the property package used for gas phase hydrocarbon systems because it provides reliable predictions of phase behavior and thermodynamic properties. For reactor modeling, we use the Gibbs reactor, also known as RGibbs, once we talk about the Aspen Plus nomenclature. Unlike the conventional reactors, the Gibbs reactor does not require reaction equations. Instead, Aspen Plus minimizes the Gibbs free energy of the system and automatically predicts the equilibrium composition. This makes it particularly useful when multiple reactions can occur simultaneously and the exact reaction pathways are known. Now let's see under what operating conditions these hydrocarbons are formed. The Gibbs reactor is operated at a temperature of 700 degrees Celsius and at a pressure of 2 bar. These conditions provide sufficient thermal energy for carbon and hydrogen to react and form a variety of hydrocarbon species. At equilibrium, Aspen Plus determines the most stable distribution of products based on thermodynamic principles. The resulting product streams typically contains methane, ethylene, and several higher hydrocarbons depending on feed composition and operating conditions. So now let's move to the Aspen Plus and implement this simulation. The first thing is to create a new simulation and specify all reactants and potential hydrocarbon products. So we will add the components one by one: carbon, hydrogen, then CH4, C₂H₈, C₂H4, then C₂H₂, then C₃H8. Now we will add C₃H6-1, which is cyclopropane, C₃H6-2, which is propylene, C₄H10-1, which is N-butane, C₄H10-2, which is isobutane, then C₄H8-1, which is 1-butene, C₄H8-2, which is cis-2-butene, C₄H8-3, which is trans-2-butene, and C₄H8-5, which is isobutylene. If we add the components or if we edit the component IDs here, some of the components would not have been visible. So I have entered their formulas or alias so that they are now visible. So you can take the name like 1C3, it could be 2C3, C3, and we can rename it. Then 1C4, 2C4, then 1 or IC4, 2C4, 3C4, and 5C4. So these are the components that are defined over here. Then we go to the methods and specifications. We will select RK-Soave. For this, we need to change the filter to all, and then RK-Soave is selected. Then click on this next, and then click on the run button so that the results are now available and we can safely proceed to the simulation environment. Now we will select the Gibbs reactor as had been given to us in reactors. This is the Gibbs reactor. Let's say we name it as reactor, Gibbs reactor actually. Two materials connections, hydrogen and carbon streams, which is represented as C, and the products, which is name is placed, rearranging it, or maybe showing carbon here, and hydrogen air control A plus control B to adjust the simulation or to adjust the flow sheet. Now click on this hydrogen, and we have been given that the feed is at 25 degrees centigrade 2 bar, and it is pure hydrogen of 100 kmol per hour. Similarly for carbon, 25 degrees centigrade 2 bar, and carbon of a total molar flow rate of carbon as 100 kmol per hour. Then we will go to the reactor. In the reactor specification and calculation options, we want calculate phase equilibrium and chemical equilibrium. The pressure is 2 bar and the temperature is 700 degrees centigrade. That is what we have to define. Then click on this run button, and we will now wait for the results that are now available. So the reactor is converged. We will go to the stream specifications or stream results to see that how much conversion has been obtained to us. You can see 700 degrees centigrade 2 bar pressure, and now in mole flows you can see that carbon is completely consumed in the system while a bit amount of hydrogen is left here. 7 kmol per hour of methane is produced, 14.7 kmol per hour of ethane is produced, ethylene 15.5888, acetylene 7.3. Accordingly, you can see the molar flow rates of all the species that have been generated in the system. Similarly, if you look at the mole fractions, you can see that in the major quantity, C₂H₄ has been produced, followed by 2-C3, which we has called, which was C₃H₈-2. So you can see that multiple hydrocarbons are generated from an elemental reaction of carbon and hydrogen at elevated temperatures, and you can see these are generated in multiple amounts. The simulation results reveal the thermodynamically favored products under the specified conditions. Such equilibrium simulations are extremely useful for preliminary process design, reaction feasibility studies, and process optimization. If you found this Aspen Plus tutorial helpful, don't forget to like the video and subscribe to the channel for more chemical engineering and process simulation tutorials. Let me know in the comments which Aspen Plus simulation you would like to see next. Thank you for watching, and I will see you in the next video.